So it is really important you understand what we mean by graphing a two-variable function. Whenever we try to graph a function in two variables, we want to think of that graph as being something inside three-dimensional space. The way that works is that your two independent variables are your x, y variables, and they correspond to points on the xy plane or in the xy plane. Your output of your function is going to be the third coordinate, the z variable, the dependent variable. Notice that every point in three-dimensional space has three coordinates, and you can find all three coordinates for the graph by just plugging in the value for x, the value for y, and your x and y's into your function g to figure out what the z coordinate is. Now, doing this by hand is a lot of work, so you could just do it in a graphing calculator, and in something like GeoGebra, that's not so bad. You could just say g of x equals the function as we wrote it down on the piece of paper. GeoGebra understands what you mean, and it automatically generates this Ripley function. Now, it's not giving you every single point when it generates this graph. It's doing an approximation to save its computational power, in which case you get a graph that's more Ripley than it really should be. But if you want to graph a point or verify that a point is on this graph, you can say, well, what happens when I set my x equal to, say, 1, my y equal to -2, and I want to know what point on the graph that would be. I would literally just have my x coordinate be 1, my y coordinate be -2, and my z coordinate be the function value evaluated at 1, -2. That's the point A, which may be hard to, oh yeah, you can see it down there on the bottom. Okay. Maybe I wish to graph the curve that's on my surface, z equals g of x, and also on the condition that my x squared plus y squared equals 4. So this is a circle inside the domain. I want to find the order triplet of x, y, z points that describe this curve. Then I do this by defining an parameterized curve for my x coordinate and my y coordinate that describes this circle over here. Now, the circle is familiar enough for me that I know a very useful parameterization that'll work, but say I didn't know a useful parameterization, I can still use algebra techniques to find a parameterization that's maybe good enough in some case. What I mean by that is, well, if I know nothing else, I can try to solve for y using algebra techniques, which means I isolate my variable, I take the square root to get rid of that square, and I might realize in that particular case, if I'm taking the square root, I have two sets of solution, a positive version and a negative version. So in my domain, this equation represents a circle inside my domain, because that's the equation of a circle, and I'm allowed to plug in those x's. And I'm only concerned about that particular circle. By using this algebra technique, I get two different parameterizations for this particular circle. The first parameterization with the positive square root that I got algebraically represents the upper half of the circle. The second parameterization with the negative square root represents the bottom half of the circle. With both of these two different parameterizations, I get the entire curve covered. But I don't really want to know just what the equation for the curve or graph a curve inside the domain is. I want to know what it is on the surface, which means I have to see what is the z coordinate for these particular points. So what I do in this case is I take my parameterized curve inside my domain, and for the third coordinate, the z coordinate, I just substitute my x and y parameterizations into my g function. And I algebraically simplify if I can, and in this case I can. And in this particular case, I get that my z coordinate is always equal to sine of 4. I can graph this now in GeoGebra to see what it looks like. There are a few ways to graph parameterized curves in GeoGebra, but GeoGebra does have a curve function. So I start typing, see that curve function comes up, I press the arrow over, and this one, the first one says I give two coordinate expressions, and then I give the parameter variable and so on, and where the curve begins and ends. Actually, I want three expressions because I'm talking about three coordinates. So I'm going to click on the second one. The first entry is my x coordinate, which I just want to be a t. The second entry is going to be my y coordinate, so that's the square root 4 minus t squared. My third coordinate is just the sine of 4. I did the work on the paper, so I know what it is. My parameter that I'm using in this case, I want it to be t, so I'm going to put a t here. My initial start position is a -2. My terminal, or my end position, is a 2. I press enter, and to make it easier to see the curve, well, let me just zoom in. That is a curve that is on my surface that corresponds to, it doesn't look like it's on the surface, but it should be on the surface, unless I had an error with, oh, I think I know what happened. I realized what happened. Here it says 4 degrees, while here it is in radians. GeoGebra, if you don't put in a number, GeoGebra thinks you're talking about radians if you put in variables. If you do put a number, apparently assumes you're talking about degrees. So I'm going to click on here and get rid of the degree symbol and hope it interprets it properly. Haha, it looks like it did. And you can now see the curve rests on the surface right over here.